In this lecture, we will look at Clausius inequality. This is an important mathematical statement which laid the foundation for entropy. So in the previous lecture, we had introduced entropy in an elementary fashion. We had analyzed a Carnot cycle and then looked at the 4 segments of a Carnot cycle. And when you do that, these 4 things add up to 0, which seems to indicate there is some quantity called Q by T. Okay, we're not going to interpret, we're going to just call it entropy, which when you sum it over all 4 segments adds up to 0. Okay, so in an analogous manner, we've already seen with first law that internal energy also adds up to 0 in an analogous manner. So whenever you say something is a state function, that means that's supposing a material is at this point in phase space, it can go wherever, and when it comes back, it has the same property. Okay, so that has certain special features, right? So state functions have a certain feature of it being property of the material. That's what we saw in the last lecture. So Clausius, if you notice this form, okay, so the early form of entropy came from analysis by Clausius. As you can see, he seems to be a very serious scientist. He's considered to be one of the founding fathers of thermodynamics. He came up with an inequality which seems abstract, but when you analyze it, is not that abstract. Okay, so this is the statement, but no point in trying to explain that. We'll see how Clausius arrived at that statement. So to do that, we have to go back to our heat engine. Okay, so we first look at reversible heat engine. Okay, so this notion of reversibility is so important in thermodynamics. Even though no real process is reversible, this notion of reversibility helped prove various versions of second law of thermodynamics just by pure logic. Okay, so this idea of reversible heat engines is very, very critical. And for a reversible heat engine, we already saw these 2 things, right? So it's a work generating device. Therefore, the heat taken up from the hot reservoir minus the heat rejected to the cold reservoir is greater than 0. And we already proved this in few previous lectures. So what is new here is we are getting into more irreversible processes. Okay, so when you say something is irreversible, let's say irreversible heat engine, not all heat engines are irreversible. Okay, if you talk about the actual heat engine, it's an irreversible heat engine. For the same amount of heat that is taken in from a hot reservoir, the actual heat engine would produce less work compared to a reversible heat engine. This is one form of second law in some ways, right? So just by first law balance, we can say that the heat that is rejected by the actual heat engine, AC refers to an actual heat engine, is more than the heat that is rejected by a reversible heat engine. So this remains true for both a reversible heat engine and an actual heat engine. What is different about an actual heat engine is these 2 add up to 0 for a reversible heat engine. We saw why in the few previous lectures. Because of this, that is the heat rejected to the low temperature reservoir being more in the case of actual heat engine, this quantity, okay, which is the corresponding quantity for a reversible heat engine is adds up to 0, but for a real actual heat engine, which is an irreversible heat engine, these two is less than 0. Okay, this just follows from putting this and this together to get this. Okay, so whenever we are analyzing heat engine, we can do all these things in reverse. We can also think about a refrigerator or a heat pump. What does a refrigerator do? You take up heat from a low temperature reservoir and then give a certain amount of heat to a high temperature reservoir with work having been done to this system, right? So an irreversible refrigerator, an all actual refrigerator in reality are irreversible heat engine, for the same amount of heat that is taken in from a low temperature reservoir, the work that has to go into an actual refrigerator is more than the work that goes into a reversible refrigerator. Okay. Again, from first law of balance, this follows that the heat that is rejected to a high temperature reservoir by an actual heat engine is more than the heat that is rejected by a reversible refrigerator. So this follows that is because work is incorporated into this cyclical system, this turns out to be less than 0 for both a reversible refrigerator as well as a reversible actual refrigerator. But what is different again, just as we saw in the heat engine analysis, is this is true for a refrigerator as well as a heat pump. But incorporating this inequality and putting this together, what we see is that these two add up to, when you add up both these quantities, this is less than 0. So why is it, how do you interpret this negative sign? Okay, this is the heat intake by this cyclical system. Okay, this is the heat rejected. Okay, so there is a negative sign here, there's a positive sign here. Okay, so both these things, when you put them together, it is less than 0. Okay, so this indicates a cyclical process, right? So cyclical process so both the heat engine and the refrigerator behave in the same manner. So Clausius proved that for all processes, okay, so this cyclical integral of this quantity, which we saw in the previous lecture itself, this quantity has something to do with entropy. The cyclical quantity can be 0 for a reversible process, but less than 0 for an irreversible process. Okay? So that's the way Clausius argued to come up with the inequality. So where do we go from here? We, having introduced entropy in an abstract manner, using cyclical processes, we would go into systems which are not cyclical. If you actually look at engineering thermodynamics, all the processes or many of the processes which we are looking at are not going to be cyclical. So we want to be computing entropy in such processes. So this would take a few lectures. We will do a lot of case studies on how to compute entropy in many pertinent scenarios. Thank you.